Yeah, welcome to the another video on VLSI design. In this video, we are going to derive the equations related to the all three regions of operation of the MOSFET. Prior to this, in the last video, we have discussed three regions of operations, namely cutoff region, linear region, and saturation region. So in this video, let us go through the details of those regions, and further we'll derive the drain to source current in each of these regions. So the topic of today's video is long channel current voltage characteristics. So we are going to derive the IV equations related to the long channel. First and foremost, let us go through the three regions of operations that we have discussed in the previous class. MOS transistor, metal oxide semiconductor field effect transistors, can be operated in three regions, namely the first region is going to be the cutoff region, or this can be called as sub-threshold region. In this region, the transistor is considered to be off because the gate to source voltage that we apply, VGS, which is less than the threshold voltage. Typically, threshold voltage is 1 volt. So therefore, transistor is turned off. So when the transistor is turned off, ideally there should not be any current flow between the source and drain. So the current flow through the transistor is considered as 0. So let us mark it as IDS. Current flowing through the transistor between drain and source is considered as 0. And in this mode, since the transistor is off, we are not going to use for any applications, but here we mainly use as an off switch. Okay. Further, we have the second region of operation is linear region. In the linear region, the transistor is turned on because the voltage that we apply here, gate to source voltage, is greater than the threshold voltage. So this forms the channel, but the drain to source voltage is not a large voltage. So we apply a drain to source voltage VDS, which is less than VGS minus VT. Okay, this we'll call as VGT, capital VGT. So drain to source voltage is going to be very small. So with this small drain to source voltage and VGS greater than VT, these are the conditions required to operate NMOS transistor in linear region. So in this region, the transistor is on. The current flow is proportional to the voltages VGS and as well as VDS. So let us write here the drain to source current in this region is now a function of both VGS and VDS. Okay, as long as VDS is small and VGS is greater than VT, the transistor will be operated in linear region, and the current flow, that is drain to source current, is now is dependent on gate to source voltage and drain to source voltage. The current flow in this region is governed by the following equation. We'll derive this equation in a couple of seconds. So IDS, drain to source current, now it depends on mu n into COX. This is called as process parameters. Mu n is mobility of N transistor. COX is oxide capacitance. W by L is nothing but the geometry of a transistor, width of a gate or width of a transistor, and L is nothing but length of the transistor. That's the distance between source and drain. And within the bracket we have VGS minus VT. This is called effective gate voltage, or already we labeled as VGT. Okay, that is VGS minus VT, and that's multiplied with VDS minus VDS square by 2. So this is the drain to source current equation in the linear region, and this equation is valid only in the linear region. And we have another equation for the saturation region. Okay, let's move on to the saturation region. The saturation region, again, transistor is on because here also we apply VGS, which is greater than the threshold voltage, but VDS is very large in this case. VDS is greater than VGS minus VT, or this can be called as VGT. So here These are the conditions required for the transistor to operate in the saturation region. The current flow is proportional to the applied voltage VGS, but here the current flow is now independent of VDS. So increasing drain source voltage or decreasing drain source voltage doesn't affect the drain source current. Now the moment we apply this condition, the transistor moves to saturation region, and now current becomes only dependent on VGS. It becomes independent of VDS, that is shown with the help of drain to source current equation. So the current in this region, saturation region, is governed by this equation. So IDS, drain to source current, equals mu n into COX. So we already explained what is mu n. Mu n indicates mobility. COX is the capacitance, oxide capacitance or capacitance per unit area, and WL is the geometry of a transistor, 1 by 2 into VGS minus VT whole square. So this shows that in saturation region it follows a square law. So these are the equations related to each of these regions. Now let us derive the equations relating the currents and voltages for an NMOS transistor in each of the regions that we have shown. Though we have mentioned the equations here, but we will derive each one of these equations separately in the various regions of operations. First, we'll assume a couple of things before we proceed to the derivation. The assumption is we assume the MOSFET is of a long channel, and therefore the long channel model, also called as a Shockley model, is going to be assumed in this derivation. The long channel model also can be called with other names like ideal model or first order model or Shockley model. These are the various names given to the long channel model. Assuming that MOSFET is a long channel, we derive the equations for drain to source current in various regions of operation. So what are the assumptions that we go through in the long channel model? The first assumption is the channel length is going to be long. Okay, so what do you mean by channel length? Channel length is nothing but the distance between the source and drain that we indicate with the capital L. So channel length in this long channel model is going to, we assume it as a long. Okay, so that is the first assumption in the long channel model. And second assumption is going to be lateral electric field. Shortly we can call as E lateral. That's going to be considered as low here. Lateral electric field is nothing but it's electric field that is between the source and drain. The electric field between the source and drain, or lateral electric field, is considered to be low in the long channel model. However, the lateral electric field cannot be taken as a low for the devices such as nanometer scale devices. Okay, so this has to be noted. Okay, for nanometric devices, so the lateral electric field cannot be considered as low, only for long channel model. So lateral electric field is considered as 0. The third assumption is this provides, the long channel model provides idealized current voltage relationship. It's not a practical current voltage relationship, but it's an idealized current voltage relationship that it provides. And later this IV relationship that we derive here can be refined further for the high electric fields, and also leakage currents can be taken care in those IV relationship that we are deriving right now. So the fourth assumption is the transistor turns on when we apply gate to source voltage greater than VT. This is the assumption, fourth assumption that we are making. When we apply gate to source voltage greater than threshold voltage, which is typically a 1 volt, the gate attracts the carriers to form a conducting channel below the silicon dioxide. This we have seen in the operation. So body is made up of the holes, majority charge carriers, and minority charge carriers are going to be the electrons. So when we apply gate to source voltage far above the threshold voltage, that attracts the charged electrons, especially below the silicon dioxide, that forms a conducting channel or N-type channel or inversion layer below the silicon dioxide. The fifth assumption is the current flow between the drain to source is determined by the charge in the channel, the quantity or amount of charge in the channel, and the second is the rate at which the charges move between source and drain. So these are the two things which are most essential in order to calculate the drain to source current. So let us work out one by one here. How do we find the charge in the channel? So charge in the channel is given by the equation. This is a standard equation we use here. there's a standard equation is charge equals capacitance times the voltage. Using this, let us apply this standard equation to the MOSFET. So using this standard equation, the charge in the channel is given by Cg. Cg is nothing but gate capacitance. That's multiplied with VGC minus VT. So please make a note here. VGC indicates it's a gate to channel voltage. It's not VGS, it is a VGC, gate to channel voltage minus the threshold voltage. And let us call this as equation 1. So let us define each one of these parameter. Q channel or charge in the channel, that is meaning of a Q channel. Cg is nothing but capacitance between the gate and the channel, that is the Cg. VGC minus VT is nothing but the voltage attracting charge to the channel or inversion layer beyond the minimum required to invert P to N. On and above required the charges to invert P to N, whatever the voltage we have, that is nothing but VGC minus VT. And let us assume that voltage at the source as Vs and voltage at the drain as Vd. Now with the help of this we can calculate what is the average channel potential. Okay, so Vc, okay, let us calculate, work out the equation for this. Vc is nothing but average of Vs plus Vd or Vs plus Vd divided by 2, average of these two voltages. So that is the channel average channel potential. And this above equation, this channel potential equation can be rewritten as by adding and subtracting the Vs here. So we can rewrite this equation as like this: Vs plus Vs minus Vs plus Vd by 2. And this Vs and Vs, that can be written as 2 times Vs, but Vd minus Vs can be written as Vds. So this equation Vd minus Vs, this, if I put a bracket here, so this bracket here, so Vd minus Vs, that can be written as Vds, so it becomes 2 times Vs plus Vds divided by 2. And splitting this into separate terms, we get channel potential as Vs, 2 will cancel out here, plus Vds divided by 2. That is the equation for channel potential. Now the mean difference between the gate to channel potential, that is VGC, is worked out as follows. VGC is nothing but its difference, Vg minus Vc, the voltage at the gate minus voltage at the channel. But we already know what is the voltage at the channel, which is Vs plus Vds by 2, that is rewritten here, and that can be substituted in the place of channel potential. So therefore VGC equals Vg minus Vs plus Vds by 2, and this can be mathematically, this bracket can be removed here. So VGC is equal to Vg minus Vs minus Vds by 2, and Vg minus Vs can be written as Vgs. So therefore VGC equals Vgs minus Vds by 2. So this is the equation from a gate to channel. The voltage potential between the gate to channel is given by gate to source voltage minus the drain to source voltage by 2. Now let us apply the gate capacitance model to the NMOS transistor and derive equation for the gate capacitance. The gate capacitance can be modeled as a parallel plate capacitor. We know the standard expression for the parallel plate capacitor. The capacitance value is given by epsilon, which is the permittivity of the free space, into area by the distance between the two plates. Okay, so let us now apply this standard parallel plate capacitor equation to the MOSFET. So let L be the length of the gate, that is the distance between the source and drain, that is the gate distance. Distance between gate and drain and source. And W is nothing but width of the gate. Okay, so TOX is the thickness of the silicon dioxide. Epsilon naught is permittivity of the free space, whose value is 8.854 into 10 to the power of minus 14 farad per centimeter. And KOX is nothing but it's a dielectric constant of silicon dioxide, whose value is 3.9. And now with the help of this standard equation, C is equal to epsilon A by D, let us apply to the MOSFET. So we have here the equation Cg, which is a gate capacitance, equals KOX already defined here, which is a 3.9 silicon dioxide dielectric constant, into epsilon naught is a permittivity of a free space, and into W by L by TOX. Okay, this resembles like epsilon into A by D. Okay, that is how the parallel plate capacitor equations appears to be. Now let us try to rearrange each one of these terms. This KOX into epsilon naught absolute permittivity can be shown with epsilon OX, and Let's see what we get from this. So CG becomes now epsilon OX into WL by TOX. Now this ratio epsilon OX, this particular ratio, okay, so we show as this as a COX. So therefore, COX CG equals COX into WL. That is the equation number 2. So now with this equation, the carrier in the channel is accelerated with an average velocity. This is actually the CG equation that is considered as gate capacitance equation. Okay. Now let us move to the velocity calculations. Before that, I just want to show you the diagrams related to this, all this, voltage and capacitor values. So here we have a detailed diagram that shows various voltages and the capacitance. As you can see here we have a voltage at the source, we have labeled it as Vs, and voltage at the drain we have considered as Vd, and there is a VGS, which is nothing but gate to source voltage. This is the voltage applied between the gate and the source. And there is a VGD, which is a voltage between the gate and the drain, that is a voltage. And CG is nothing but it's the gate the capacitance, that is shown with the capacitor symbol here. And VG is nothing but voltage at the gate, and VDS is nothing but voltage between the drain and source. Okay, so in this way, all these terms, whatever we have shown here with the formulas, that can be presented on the MOSFET also. Okay, let's now follow the velocity. Let's apply the velocity terms to this transistor. The carrier in the channel is accelerated. The carriers, in the sense, the electrons in the channel is nothing but which is below the silicon dioxide, is accelerated with an average velocity of V, and which is proportional to the lateral electric field. We already defined lateral electric field. Lateral electric field is nothing but it is the field between the source and drain. And now mathematically we can write that the velocity is proportional to the lateral electric field, and this proportionality can be removed, and that can be shown as a constant. The mobility is going to be the constant of proportionality, and so therefore this equation becomes V is equal to mu into E. Let us consider this as equation 3, where mobility of electron is going to be, it lies in the range of 500 to 700 centimeters square per volt second. That is the unit of the mobility. But we know that velocity is equal to distance by time. So velocity is small v, which is equal to distance with reference to MOSFET is channel length L, and time is going to be the small t. We can derive the time equation from this. Time is equal to distance by the velocity. Time is nothing but it's the time required for the carriers to cross the channel or move from source to drain. However, the electric field is nothing but it is the voltage difference actually. Okay, so voltage difference, so between the drain and source. So VDS is now divided by the channel. So what we get to the channel length L here. So therefore, equation for E can be written as VDS by L. Okay, substituting this equation in the 3 we already defined here. So let us see what will be the new equation for the velocity. So velocity equation now becomes now mu times VDS by L. Substituting this E here in place of this. So the velocity equation now modifies to mobility times VDS by L. Now let us move to the further derivation of the equation. The current between the source and drain is nothing but total amount of charge in the channel divided by the time required to cross the channel. So mathematically that can be written as IDS equals Q channel divided by the time required by the charge carriers to cross the channel. We already know expression for the Q channel. So Q channel is nothing but CG times VGC minus VT, and T is nothing but it is a L by distance between the source and drain by the velocity. And now let us write that T substitute here, and we get IDS as CG into VGC minus VT divided by L by V. But we already know the equation for velocity is given by mu VDS by L. So therefore the IDS equation becomes now retaining the numerator as it is, but in denominator for velocity we substitute as mu VDS by L. Now we can substitute other things also in this equation, like IDS is equal to CG can be substituted as per this, and VGC can be substituted as VGS minus VDS by 2, and the denominator VDS can be this can be numerator, this L can be taken to numerator, and that becomes L square by mu VDS. And after substituting we get this. We can cancel this one of this L with this L square, and retain the rest of the things which is here. So we get the COX into W into VGS minus VT minus VDS by 2 by L divided by mu into VDS. This mu VDS can be taken to numerator, and this equation can be simplified. That is done here. So IDS equals now mu goes to numerator into COX W by L into VGS minus VT, that is as it is. Now VDS gets multiplied with this, so it is VDS minus VDS square by 2. So this is the standard equation for the drain to source current in the linear region or triode region or non-saturation region. And here the mu n into COX is called process parameter. This parameter depends on the technology. And as we already mentioned, W by L is called transistor geometry. This decides the dimension of a transistor. The transistor area is nothing but L and W decides the L and W. Okay, L indicates length of the channel and W indicates width of the channel. And VGS minus VT is the effective gate voltage, or we have labeled this as VGT. And as we can make out from this, the IDS is now a function of VDS, because we have VDS here. Also, it is a function of VGS. So IDS, any VGS increase or decrease, corresponding IDS also changes. And even the VDS also affects the IDS. Any variations in VDS, that also changes the drain to source current. So we can write here formally, this IDS is now a function of VGS and VDS. Okay. So now we can simplify these terms here. Mu COX can be called as K dash, and WL can be written as it is, and this entire term can be called as a beta. This is not a transistor beta, BJT transistor gain beta, but this is a beta is nothing but it is the very important parameter that relates transistor geometry and even process parameters. So beta is now this, if you substitute the K dash as mu into COX, that becomes K dash into W by L, where K dash is mu into COX. Now, as I told you already, the VGS minus VT can be called as VGT. Then the equation in the linear region can be simplified like this. IDS is equal to beta into VGT minus VDS by 2 into VDS. Or this can be written as beta VGT into VDS minus VDS square by 2. Okay, the same substitution what we here, instead of VGS minus VT, we substitute as VGT. So we get two versions of the equations. Okay. Now let us see that in the region of operation, each of these region of operations, how exactly the drain current can be written. For linear region, we already know VGS is greater than VT, but drain to source voltage must be less than the effective gate voltage, VGS minus VT, or this can be written as, if you substitute this entire thing as VGT, VDS becomes very, very less than VGT. So the equation for that is as follows: IDS equals beta. All those process parameter and transistor geometry we have now called by single constant as a beta. So VGT is nothing but VGS minus VT minus VDS by 2 into VDS. So this is the equation applicable in linear region. And for saturation region, VGS is greater than VT. This is a condition. But VDS also is far greater than VGS minus VT, or this alternatively it can be written as VGS minus VT can be called as VGT. So therefore VDS is far greater than VGT, or that can be equated to VD saturation. And but at VDS equals VGT, it's a point at which saturation commences. We have seen that in transistor operation, when drain source voltage is exactly equal to VGS minus VT, that is the start commencement of saturation. We say that channel has been pinched off at the drain side. So therefore this VDS can be called as VDS sat at this particular point. So the modification for this equation is now IDS equals beta into VGT minus, now in place of VDS we can substitute as VGT. So here also we have VDS, we can substitute as VGT. Therefore this complete equation can be simplified further. So after substituting here as VGT, we arrive at this equation, and after simplification we get final equation as IDS as beta by 2 into VGT square. And this is nothing but in saturation we can conclude that MOSFET behaves like a square law. Okay, so equation 8 is valid only for VGS greater than VT, and VDS is far greater than VDS sat. That is nothing but saturation region. And now we'll proceed with the two key figures of merit of a transistors. Okay, so one is current flowing in a transistor, in the on transistor, and current flowing in the off transistor. Let us first find out the on current. When the transistor is turned on, the current flowing through that is ion, which is equal to IDS, and that given by under the conditions of this VGS equals VDS is equal to VDD. When you apply voltage as this, the transistor turns on, and current flowing through that is labeled as I on, which is also equal to IDS. And we can show that as in saturation region, the on current is nothing but beta by 2 into VDD minus VT whole square. This already we derived it. That is the on current flowing through the transistor. What is off current? When the transistor is turned off, so the off current is labeled as I off, and this will happen only when VGS is 0 and VGS equals to VDD, and I off current is going to be 0. When we make gate to source voltage as 0, definitely there is no current, transistor will be turned off, though it is the voltage across the drain and source is VDD, but still the off current or drain to source current is going to be 0. Now let us summarize the equations that we have derived here. So drain to source current in cutoff region is 0, and to drive the transistor into cutoff region, we need to apply gate to source voltage less than the threshold, and region of operation is cutoff region. This is the region of operation. Okay, region of operation is this, and these are the conditions to operate transistor in different regions, and these are the drain source equations. IDS is going to be 0 for when we make VGS less than VT, and the region is called as cutoff region. IDS equals beta times VGT minus VDS by 2 into VDS. Okay, so this is the current that is flowing in the linear region, and for linear region, drain source voltage must be less than VDS side. And drain source current in the saturation region is beta by 2 into V square GT or VGT square, and the condition for that is VDS must be greater than VDS sat, and region of operation is saturation region. With that, we have come to an end of this, deriving transistor current equations in the 3 regions of operation. In the next class, we will expand with the characteristics of N channel and the P channel MOSFET devices. Thank you for watching this video.